Welcome to this lecture series in linear algebra. In this lecture, we look at the notion of the trace of a linear map or a linear endomorphism on an inner product space. And let us recall a few things. So if V is an inner product space and we have an orthonormal basis of the space, then for any vector V, we can express V as a linear combination of the EIs in the following way. So since this is a basis, of course, one can indeed express V as a linear combination of the EIs. The coefficients come just by taking inner products is the point. And this is easy to prove because you can just, write alpha I as the coefficient and then dot both sides by, let's say, EJ. And then it'll just pop out that these are the coefficients. All right, and we also need to know the notion of the adjoint of a linear map. We have recalled this several times earlier, so I'm not going to do it now. And with that, let's move on. Here are some problems for practice, and we have one star marked problem, not because it is hard, but because one can use it. We will not use it, but a certain step in a certain proof is immediate using this exercise. It is a meaningful exercise. It is just asking us to relate the matrices of a linear map with the matrix of the adjoint. And the result is that the matrix of the adjoint is the conjugate transpose of the original matrix. But yeah, one has to work with orthonormal bases for that to be true. So take this seriously and let's move on. So first we will prove a technical looking lemma. So fix an inner product space V, and let's say we have two orthonormal bases of V. Then this meaningless looking sum is equal to that quantity, where what is that quantity? That is the Kronecker delta, which is defined as 1 if k is L and 0 otherwise. So it's just a convenient notation. And in terms of the Kronecker delta, one can rephrase the definition of an orthonormal basis but just by saying that a given basis E1 up to En is orthonormal if this is equal to the Kronecker delta Ij. Right? So I'm sure you agree. And with that, now let's prove it. So here is where one could use the star marked exercise, but I will not do that. I will do it in the language of endomorphisms. And yeah, so let's start. So we define a linear map or a linear endomorphism on V by declaring right. So we just declare TEI to be Fi for all I. When I say for all I, it means that I runs from 1 to n. Okay, so since once you define a linear map on the basis elements, the linear map is completely defined. So this is a well-defined linear map now. Therefore, this expression by definition of the adjoint is equal to which is equal to that by definition of T. So therefore, this is the Kronecker delta because that was the Kronecker delta by the virtue of the fact that Fi is from an orthonormal basis. But then this is also equal to Ei Ej, which implies this is 0. But this was true for all I and j. And therefore, this is also true for all I and j. So once you fix some I and vary over j, we see that this better be the 0 vector because dotting with any element of the orthonormal basis is giving 0. So this better be the 0 vector, and hence we have this equation T star Fi is equal to Ei for all I. So or maybe if you want one more step, it just this is 0, which implies this is equal to ei for all I. Okay. So therefore, T star Fi is TEI, which is equal to Fi for all I. But that means that T star is the identity map, because T star is fixing every element of the orthonormal basis. So it is the identity map. All right. So now we have E and then subscript is L. This is equal to, because T star is identity, right? So all we have used is that T star EL is equal to that expression. Color coding will help. And this is true because if this was any vector v, we could express it like that, as we commented in the recall. Okay, so what is this? Sorry, I missed term. Right? So what is this? This is equal to that. By definition of the adjoint, which is by definition of T. And in fact, this is also Fi. So we have just used the fact that TEI is Fi. Okay. And therefore, now we can dot both sides by Ek. So EL dot Ek is this summation dotted with Ek. So we just took the summation out, and this gives us, so this is just a number, so it pops out of the inner product. All right, and this is equal to that. So what we have done is we have just moved the right term to the left side. So this is equal to that, and this is equal to that. We have switched the order here, so we incur a complex conjugate. So this is same as delta KL because this is equal to delta KL, and hence delta KL is that, and this is what the lemma was. So this proves our lemma, and now we move on. Okay, so now here is a very important statement. So suppose we have two orthonormal bases of a vector space V. Then for any linear endomorphism T, we have this sum is that sum. So what this is saying is that whenever we are given an orthonormal basis, we could form this sum, but it remains invariant regardless of which basis we choose. So that's a very nice fact, and let's prove it. So we have Fi is equal to right? This is what we recalled in the beginning. Any vector v splits that way. So we get the ith term on the right hand side basically. This is equal to right. So something is wrong. Bracket is missing. This bracket should be here. Yeah. So all we did was fi is equal to that thing, and fi is equal to that thing also. All we have done is change the index from k to l. That's all. Okay. So now we can pull out the summations and apply linearity of t to get that. So what we have done is, these are scalars, they come out as such. These are also scalars, but they come out with a complex conjugate because they are in the second slot, and the rest is just linearity of t. So just make sure you agree with this, and now we get the summation that we are interested in. This is equal to that. So we just pushed this summation inside and we get that. But this is what we evaluated in the previous lemma, and this is nothing but the Kronecker delta of k and l, which, if we use the property of the Kronecker delta, this is nothing but, this is same as that. So again, I leave this step as an exercise. So yes, so we have this is equal to that, and that proves our very nice statement. And this allows us to define the trace of any linear endomorphism. Okay. So maybe I'll just highlight one thing in all of this so that it is easier to follow, perhaps. Make these brackets and make this bracket. Perhaps the bracket earlier was not anyway correctly placed. This looks much better. Yeah. So this pink bracketed term is that. Okay. So now we can define trace of a linear endomorphism on an inner product space. So we are given such a T, and now the trace of T So you pick any orthonormal basis even up to En and then form this summation. That is the definition of the trace of T. This does not depend on the choice of the orthonormal basis, is precisely what the previous lemma was. Okay, so fine. So we have an invariant associated with any linear endomorphism on an inner product space, and it has some very interesting properties. So if we have two endomorphisms, then doesn't matter in which order you compose them, the traces are the same, and that is quite surprising to me. Alright, so let's prove this. So fix an orthonormal basis. Okay, and now by definition of trace, this is equal to the following sum. Which is by definition of the adjoint of S, which is equal to so let me explain this. Basically what we have done is this great term. So the gray terms are equal is all. Just think of this as a vector and that can be split like this. Okay, but this is equal to so let's pull the summation out, and we also pull out the scalar. But now we can put this scalar in the second slot along with this with the summation also, but let's not do 2 steps at a time. So we'll put it here. I'm going to run out of space, so I'll have to do it here itself. But we have to be careful because it's the second slot, so we need to put a complex conjugate. Okay, so I hope you followed that. And now use linearity of S star. So using linearity of S star, we can further manipulate this. All right, nothing much has happened. And now the summation over I we will push inside. Okay, but this summation can be pushed further inside, and let me again do it here itself by linearity of S, and again it helps to color code the brackets. Okay, and now let us talk about this summation that is present here. The summation that is present is this summation I equals 1 to, wait a second, I should have, no. Summation I equals 1 to n right, that summation, and we claim that this is equal to T star Ej. So that is a claim that this is equal to T star Ej. How do we prove this? Well, T star Ej is what? T star Ej is this summation. Not enough space. Right, again we are using the same fact. For any vector you can split it like this. And now use the definition of the adjoint. Okay. Now take the complex conjugate. So it matches with that. Okay, so this is T star Ej. I hope I have one more page. Yes. So what we get using this calculation is trace ST is that's what we get. I mean, we could have done this in one step. So this is trace TS. Very nice. So that proves our lemma about traces. And there's one more lemma. So this is, again, fix an endomorphism, then trace of T is the conjugate of the trace of the adjoint of T, and this is an exercise. It's much easier than the previous one. Okay. So now for the main, why we were doing this. We can define an inner product on the space of endomorphisms on any inner product space. Okay. So fix an inner product space V. Then we define a map from end V cross end V to the base field, which could be either real or complex, as follows. And before I do that, when we say V is an inner product space, it already comes with an inner product, which we denote like this. And this also, the new thing that we are defining, we will also denote like this. And that is an abuse of notation, but that is fine. There is no confusion that can arise, so it is fine. So we define this map as follows. T dot S is trace of S star T. So that's the definition. And we claim that this is an inner product. So let's prove this claim. First of all, what is this? This is trace of, but that is equal to, where this is an orthonormal basis, E1 up to En is an orthonormal basis. I'm not writing that. So this is equal to right. So this is always non-negative, and it is 0 if and only if each Ti is 0, which is if and only if T is 0. So the positivity condition that is required by an inner product is satisfied. And the other conditions, the bilinearity ones, I leave you to check. So this was the only thing that I'm going to check for this claim. Every other condition is an exercise. So this indeed is an inner product on this guy, and this will be very useful. Okay. So yeah, I think this is it. And with that, I want to end this. I will see you next time.